Classification is based on source of acid, composition of acids, strength, concentration, basicity, and acidity. First two classification are exclusively for acids. Last three are for both acids and bases. Based on source of acids, we have two categories, organic acids and inorganic acids. As the name itself indicating, organic acids are obtained from organic sources like plants and inorganic acids are obtained from inorganic sources like minerals. We know acids are proton donors. So, both organic acids and inorganic acids are expected to be consisting of minimum one hydrogen atoms in it. Along with hydrogen atom, organic acids contain carbon in it. Most of the inorganic acids do not contain carbon in it. Few examples under organic acids: oxalic acid, formic acid, citric acid, tartaric acid, etc. Most of the organic acids are weak acids. Under inorganic acids, hydrochloric acid, sulfuric acid, nitric acid are few examples. Most of the inorganic acids are strong acids. We have an exception under inorganic acid, that is carbonic acid. This is a weak inorganic acid having carbon atom in it. Based on composition of acids, we have two types, hydracids and oxyacids. Hydracids will have hydrogen and a nonmetal which is not oxygen, and oxyacids will have hydrogen and oxygen with any other element. Example, for hydracids, hydrochloric acid, hydrobromic acid, hydroiodic acid are few. For oxyacids, nitric acid, sulfuric acid are few examples. This classification is based on strength of acids and bases. Bases we mean alkali. Strength of acids mean concentration of hydronium ion in aqueous solution. Strength of alkali means concentration of hydroxyl ion in aqueous solution. Based on strength, we have strong acid and weak acid. Similarly, strong base and weak base. Strong acid dissociates almost completely in aqueous solution. Hydrochloric acid, sulfuric acid, and nitric acid are few examples. Let us understand the dissociation of strong acid in water by considering HCl as an example. Let us consider 100 HCl molecules in water. Initially, when HCl is just added to water, we won't have any H plus or Cl minus ions. After few seconds, HCl starts to dissociate. One HCl will dissociate to give one H plus and one Cl minus. In this case, since HCl is a strong acid, all 100 HCl will dissociate to give 100 H plus and 100 Cl minus. So, after the dissociation, 100 minus 100, that means we will not have any HCl molecule left in the solution. We will have 100 H plus and 100 Cl minus, meaning after the dissociation, we will have only ions in solution. Same is the logic even with strong base or alkali. It completely dissociates in aqueous solution. Examples are sodium hydroxide and potassium hydroxide. Same is the concept even here. If we take 100 sodium hydroxide, initially we won't have any Na plus or OH minus. After some time, all 100 NaOH dissociates to give 100 Na plus and 100 OH minus. After the dissociation, we won't have any sodium hydroxide compound as a whole left. We will have only Na plus and OH minus. So, both strong acid and strong base solution contains only ions in it. Weak acid dissociates partially in aqueous solution. Examples: acetic acid, formic acid, citric acid, carbonic acid, etc. All naturally occurring acids are weak acids. Let us understand the dissociation of weak acid with acetic acid. Acetic acid dissociates in water to give one acetate ion and one chloride ion. Let us consider 100 acetic acid molecules initially. At the beginning, we will not have any acetate or chloride ions. After some time, acetic acid starts to dissociate. Since acetic acid is a weak acid, only few of the 100 acetic acid molecules will dissociate. Let us consider 20 of the 100 acetic acid molecules to be dissociating. Since one acetic acid gives one acetate and one chloride ion, 20 acetic acid molecules dissociate to give 20 acetate and 20 chloride ions. So, after the dissociation, we will have 100 minus 20, that is 80 acetic acid molecules left in the solution in the molecular form. Along with these 80 acetic acid molecules, we will have 20 acetate ions and 20 chloride ions. So, acetic acid solution in water contains both ions and molecules. Same is the logic even for weak alkali. They dissociate partially in aqueous solution. Ammonium hydroxide and calcium hydroxide are few examples. Let us understand the dissociation with ammonium hydroxide. One ammonium hydroxide dissociates to give one ammonium ion and one hydroxyl ion. Let us consider 100 ammonium hydroxide initially. At the beginning, we will not have any ammonium or hydroxyl ion. For ammonium hydroxide, let us imagine 10 of the 100 ammonium hydroxide to be dissociating. Since one ammonium hydroxide gives one ammonium ion and one hydroxyl ion, 10 ammonium hydroxide will give 10 ammonium ion and 10 hydroxyl ion. So, after the dissociation, we will have 100 minus 10, that is 90 ammonium hydroxide left in the molecular form in the aqueous solution. Along with these 90 molecular ammonium hydroxide, we will have 10 ammonium ions and 10 hydroxyl ions. So, ammonium hydroxide aqueous solution will have both ions and molecules. Together, weak acid and weak base solutions will have both ions and molecules. Based on concentration, we have concentrated acid and dilute acid. Similarly, concentrated alkali and dilute alkali. Concentrated means we will have relatively higher percentage of acid or base in the aqueous solution. Dilute means we will have relatively lower percentage of acid or base in the aqueous solution. We know that HCl is a strong acid and dissociates completely in water. Acetic acid is a weak acid and dissociates partially in water. Let us consider the addition of 10 HCl to some amount of water. This would give us acidic solution consisting of 10H plus and 10Cl minus ions because HCl dissociates completely. If we repeat the same experiment with 10 acetic acid, this also will give us the acidic solution but consisting of less H plus ions because acetic acid dissociates partially. Let us imagine 20% dissociation to 10 acetic acid. This will give us acidic solution consisting of 2 H plus ions, 2 acetate ions and 8 acetic acid molecules. Going to concentrated acid and dilute acid, let us consider 1 liter water under both category. Concentrated acid just means we have to add more amount of acid. It may be strong acid or weak acid, doesn't matter. Dilute acid means we have to add less amount of the acids. So, strong acid and weak acid terms are related to capacity of a particular substance to undergo dissociation. Concentrated acid and dilute acid is related to amount of acid present in specific amount of solvent, that is usually water. Next classification is basicity and acidity. Basicity is a term related to acid and acidity is a term related to base. Basicity of acid means number of H plus ions one acid molecule can donate in aqueous solution. Acidity of base means number of OH minus ions one base molecule can donate in aqueous solution. Based on basicity and acidity, we have few more classifications. Under basicity of acid, monobasic acid, dibasic acid, tribasic acid. Similarly, under acidity of base, we have monoacidic base, diacidic base, and triacidic base. Monobasic acid ionizes in water to give 1H plus or 1H3O plus ion per molecule. Few examples and their dissociation can be seen here. Observe, for one acid molecule considered, we are having 1H3O plus on the product side. So, we say these acids are having the basicity 1. Not all the hydrogens present in the acid molecule are acidic. Example, in acetic acid, these three hydrogens are not acidic. Only this hydrogen is acidic and is capable of coming out when we put acetic acid into water. Similarly, monoacidic base means they ionize in water to give one hydroxyl ion per molecule. Few examples and their dissociation. For one base molecule considered, we are having one hydroxyl on the product side. Now we say these bases are having acidity 1. Dibasic acid ionizes in water to give 2H plus ions per molecule. Examples, sulfuric acid, sulfurous acid, carbonic acid, etc. Usually, dibasic acids dissociate in two steps. Let us understand with sulfuric acid. In step 1, sulfuric acid loses one hydrogen atom, giving one hydronium ion and one HSO4 minus ion. This HSO4 minus ion in step 2 loses one H plus, giving one H3O plus and one sulfate ion. Summing up, we can see one sulfuric acid giving two hydronium ions, meaning basicity of dibasic acids is 2. Similarly, diacidic base ionizes in water to give 2 hydroxyl ions per molecule. Examples, calcium hydroxide, magnesium hydroxide, etc. Calcium hydroxide is observed to be dissociating in one step, giving 2 hydroxyl ions. So, acidity of calcium hydroxide is 2. Apart from these water-soluble bases, we are having water-insoluble diacidic bases also. Example, zinc hydroxide. Tribasic acid ionizes in water to give 3H plus ions per molecule. Best example is H3PO4, that is phosphoric acid. This ionizes in water in 3 steps, losing 1 H plus in every step. If we sum up these 3 steps, then these ions cancel each other, giving overall equation like this. We can see here 1H3PO4 donating 3 H3O plus ions. So, basicity of H3PO4 is 3. Similarly, triacidic base ionizes to give 3 hydroxyl ions per molecule. Usually, triacidic bases are insoluble in water. So, we have not mentioned the presence of water for this ionization. Examples are aluminium hydroxide, ferric hydroxide, etc. Acidity is 3 for these bases. When HCl is mixed with water, it results in the formation of hydronium ion and chloride ion. Both water and HCl are polar covalent molecules. In water, we have positive pole on hydrogen and negative pole on oxygen. In HCl, positive is on hydrogen and negative is on chlorine. When water and HCl are put together, lone pair of electrons on oxygen attacks on hydrogen of HCl, breaking HCl bond like this. This results in the formation of hydronium ion and chloride ion. For the bond formation between oxygen and hydrogen, since the electrons are contributed only by oxygen, this bond is called as coordinate covalent bond. When ammonia is mixed with water, it gives ammonium ions and hydroxyl ions. Both ammonia and water are polar covalent molecules. In ammonia, hydrogen carries partial positive charge and nitrogen carries partial negative charge. In water, hydrogen carries partial positive charge and oxygen carries partial negative charge. Lone pair of electrons on nitrogen in ammonia attacks on the positive hydrogen of water, resulting in the breaking of OH bond. This gives us ammonium ion and hydroxyl ion. In ammonium ion, newly formed NH bond electrons are given by nitrogen alone. So, this NH bond is recognized as coordinate covalent bond.